Hello and welcome back to another coding session with Mr. Jacob. Today we want to work on another PixelLoop project as, for example, this fireworks display that we implemented before. I will link the video up there if you are interested in that. Or like this, for example, breakout game, which is actually both working in the terminal. So we can actually have something like that in a terminal window, or something like our sense simulation, which not works in a terminal yet, but is a nice little thingy that we created with our PixelLoop engine as well. I will link that up there as well. So if you're interested in that topic in general, you will find a lot of different videos on this channel regarding the PixelLoop engine, as well as videos based or showing the development of the engine itself. So what we want to do today is we want to create something like that. I found that on the internet a couple of years ago when I was building a pixel display thingy with an ESP microcontroller and some of those nice little LED matrices. And actually someone created a Tetris-based clock display. And I recently thought when I needed a clock display within a workshop to show like we now making a pause of so and so much minutes, I thought it would be great to have something like this to be simply able to run it in the terminal and then show the time or the remaining time in a nice way. And I remembered this one and I thought, why not implement something like that in our PixelLoop engine? So let's get right into it. We have our PixelLoop engine right here. We have most of our projects with it within here as well. Currently, this is a kind of a monorepo thing where I want to develop this PixelLoop library and engine a little bit further before releasing it as a simple to use library within Cargo.io itself. But if you're interested in that, just check out the repository, which is linked down below. We have our trivial CLI demo here, which actually is, let me quickly run this. I need to go one level up, I guess. Run bin trivial CLI demo. And when this is actually ended, we want to reset our shell. And this is our trivial CLI demo where I can, with our cursor keys, move around this this violet rectangle there, and the rest is just flying around. And yeah, I can quit that, and then we are back in our shell again. This is actually quite a good starting point for us to get going developing a new project. So I guess we will simply copy that one. So trivial CLI demo, and we will copy that to Tetrominos CLI maybe? Yeah, Tetrominos CLI. Because all those little things that a Tetris game is made up of are called Tetrominos, those building blocks. So yeah, I guess that is a nice name. And then I guess we need to go into our cargo toml and kind of add a new binary here. We could copy this one, I guess, and this one would be Tetrominos CLI, and it will be Tetrominos CLI here as well. And now if we call this run again and open up Tetrominos CLI, it should show us exactly the same as our trivial CLI demo. Perfect. So now we can go into Visual Studio Code and open up our Tetrominos CLI main there and clean it up a little to have a good starting point with this thing. So I guess we don't need this box. It's just a holder there for the thing that we are rendering before. We will need some sort of state, but I will leave it empty for now. We will see what we will put in there to start with. Actually, a state is always used within our PixelLoop engine to be transported through the engine. So there are different operations like the rendering and the updating of stuff, and it's always transporting this state through. So everything that we encapsulate in a state, we will be able to update. So this would be our initialization code. which gets the terminal size, then it initializes the canvas, it sets a maximum refresh limit because we don't need to refresh the terminal as much as we could, because I will link that video above as well. We optimized our terminal renderer a little time ago and made it so fast that it actually could kind of render something like 40,000 frames or so per second, and we really don't need that, so we introduced a refresh limiter here. Then we initialize our state. We initialize an input state handler, which we can use to actually get key presses and stuff like that. That is actually part of our PixelLoop engine as well. And then we run the engine with 60 updates per second. And we have here our update function, which actually just checks for the key press of Q to then exit. And then we have all those other key press event check thingies there that are currently moving all those boxes around. We don't need that anymore, so let's remove that. And let's maybe put a comment here, like something like update here, so that we know where to put this code. Yeah, we introduced some benchmarking code the last time when we optimized our terminal render. We don't need that as well. However, I guess we want to clear our screen to black. Yeah, that's quite nice. We don't want to render our boxes there anymore, so let's just remove that and let's just put a marker there like render here. And let's remove the benchmarking code as well. So where did I remove, I guess, some sort of, oh, I guess I need to return okay here. Yeah, okay, so I could have actually, of course, prepared that beforehand, but I wanted to use the time. Let's quickly remove those imports here, to use the time to go over it quickly with you, just to give you some sort of introduction again to how this actually is working. So as you can see now, we have something like 57 lines of code there now, which is just our initialization code, which is very minimal. So essentially what is important to us is this function, which is our update function, and this function, which is our render function. Our PixelLoop engine works in two different cycles, kind of. It automatically synchronizes the update and the render cycle loops in a way so that we kind of get a guaranteed frame time. So if we tell it to have 60 updates per second, it will always try to give us exactly this update time so that we can properly animate stuff in a very precise and consistent way without always incorporating something like the calculated delta time and stuff. And it will automatically do this regardless of how many frames it is capable to render. If it's not capable of calling update 60 times a second, then of course that's a problem and shouldn't persist throughout the application. But if it occurs in certain situations, it can handle that as well. So again, if you're interested in how we do that, just take a look at the video, which I am linking down in the description, as well as up there in the corner where we develop this engine. Actually, it's actually a quite nice and essentially very easy way to implement something like that once you have an idea on how to do that. But it's a great way to do something like that. So I guess now we can get kind of started. I guess we will need some sort of state there. First of all, I guess we need some data structures because we need to somewhere hold our tetrominos. So I guess we will get going by simply having some tetrominos which fall down the screen and are kind of calculating their collision with each other and are drawn, so that we have a starting point to then, based on that, create the time and the clock that we want, because we need that logic anyways. So I guess we will start with something like a tetromino. And the tetromino will most likely have an X position, which is, I think, in our engine an i64. I'm not 100% sure if it is an i64 or iSize. I guess I refactored that at some point, but we will see. Haven't done a lot of stuff with this engine for quite some time now. So maybe we will need to figure some stuff out while going along. So this thing will need a position of some sort. I guess it will need some sort of form, maybe something like tetromino form. I'm not 100% sure how to call this actually. So what we want to, or what we will need is, let's see, tetromino. Let's quickly Google that. So those are actually those different tetromino forms that exist. And as you can see, there are different shapes or forms. And maybe shape is the better name for it. So we need to somehow differentiate those. And I guess we will start with one of those. Why not? Let's still start with this L shape. So let's simply go there and let's see tetromino shape. So I guess this will be an enumeration, and we will have something like tetromino shape, I guess. And yeah, what did I say? L shape we would have. Yeah, let's for now just only start with this L shape, and then we can work with that and base our further work on that. Okay, we now have that shape, so I guess, shape, I should have renamed, not chapter, but shape, come on, shape, we should have renamed that as well. So what do we need now? We have a container to store our tetromino, we have the shape type there, we now need to kind of put that somewhere into our state, but maybe we want to encapsulate that further in some sort of board to display, some sort of game board, because I guess we will need some sort of encapsulation later on to display the different digits. Do we need to split them up? I don't want to think about that yet. So let's just do something like board here, and board holds, what could board hold? It holds tetrominos, which is a vector of tetromino, I guess. Yeah, okay, so our state will then have a board, which is a board, and we need an impl of board. So impl board pub fn new, at least we will need, and it returns a self. And this self will simply do tetrominos. Come on, with an empty vector there, just initialize it empty, and we need a way to add a tetromino, I guess. So actually, I think I want to kind of encapsulate all of that tetromino logic. So within this board, so I guess we will do something like pubfn add tetromino, and I think I will give this an X coordinate, which would be an I64, Y coordinate, which is an I64, and a color most likely. Come on, color, which would be a color and a shape, which is a tetromino shape. Or should I? Wait, those things don't have a color yet, do they? Yeah, that's another another thing that we need to accommodate. They need a color. So those things have a color, I guess. Okay. So when we add this tetromino, we can actually, we need to put in a mutable self reference here, so that we can say self.tetrominos push, and we push a new tetromino in there, which has the X, the Y, the color, and the shape, I guess. We should be able to simply put that through so that we now have this tetromino there. And yeah, let's see. So this will actually only be some sort of data struct to hold the tetromino information. We won't implement methods on it, I guess. I'm not 100% sure, but we will see. Okay, so now we have the capability to add a tetromino. So I guess we could implement that already. We should now implement the state creation. So the state now has a board, which we just gave a new function. So this should actually still compile. Yeah, it does. So I guess now we need a way to render our tetrominos. So do we actually... Yeah, the question is, do we implement that on the tetrominos or on the board? And I guess we will implement that on the board because the rendering code for each of the tetrominos isn't that complicated. And it kind of gives us flexibility to have maybe later on multiple of those boards as digits. And then we could actually update and animate them differently. Yeah, that kind of makes sense, at least in my head currently. Let's see how this actually turns out. So, so we actually will have this board. Now we have a tetromino, so what we now need is a pubfn render. So we want to render it, and we want to render it into a specific canvas, I guess. So C canvas, and canvas is should be here now. Canvas first of all is self reference, and then a canvas which is a mutable reference to this C. And this canvas actually is a PixelLoop canvas. That's actually our data structure, our abstraction where we render into, and which then does all the shell stuff and the console stuff that we need to display this within our terminal. Okay, so we need to render that. So I guess we need to do a for tetromino. We need the shape, the X, the Y, and the color, I guess. In self tetrominos iter. So let's just get those out of there and iterate them. And I guess then we want to do a match shape, and we want our editor to fill those. Currently we only have one of those match arms. Makes sense. However, let's just create a default match here with a panic render implementation for the shape not implemented yet. And we put in there the shape, and I guess that we then need derive debug here so that we can actually print that out. It still doesn't like that. Match arm body without braces. Yeah, while parsing. What's the problem there? Wait, what is this? What is the problem? Unreachable pattern. Yeah. Okay, that's okay because we don't have other tetromino shapes yet, but we might in the future, and I just want to be sure that we then get a proper error. And yeah, so to render the L shape, so the L shape actually is this thing. So where would we actually base our coordinate? So if we have it at the XY coordinate, is it this pixel here or is it this pixel here? I guess as we are always falling down, we will always need to kind of calculate things relative to the bottom. So I guess we will kind of define the positions based on the bottom the leftmost bottom position or something like that. Not sure how we are going to work with those shapes then. Those, no idea what is that kind of shape. Thingy, rotated S shape or something like that. Okay, so I guess let's for now think about this like we have the XY position in the bottom corner. So what we need to do to render this actually should be quite simple. Canvas, it has something like, yeah, filled rect, perfect. So we should be able to do like we need from the X coordinate down in the bottom left corner then. So that would be our X, and we would need to go up 2 pixels. And the Y would be just our Y, and the width would be 1, and the height would be 3, and the color would be our color. And then we would need to go to the right, so 1 pixel to the right. So actually then that is our X. Oh, wait, it's not X that we need to move, it is Y that we need to move up. And here we are just going 1 pixel to the right on the X. Exactly, we are staying on the Y, and we are doing a 1 by 1 filled rect. Yeah, that should actually render our tetromino. So maybe let's try that by creating one. Maybe just we could introduce a key handler here. So if input is key pressed, keyboard key space maybe. So let's remove that comment. Let's add a fix me here only for testing, remove later. So in case this thing is actually pressed, we could create a tetromino at a specific position and just add it to our board. So let's just go ahead and get our state, get the board in it, do add tetromino at, I don't know, 2020 with a color of red maybe, and a tetromino shape L shape, please. Something like that. Okay. So, and then in the render cycle here, we need to iterate for we simply tell the board to render itself into the given canvas. Does that make, yeah, that makes sense. So let's see. Let's actually see what happens if we run that. So if I now press space, something appears on the screen, but it seems I have done something wrong with our positioning calculation there. Okay, but at least something appears on the screen. That's already a progress, I would say. So where did we actually do this? So the X coordinate is the bottom left corner of this L shape. So we are actually going ahead and doing X. Yeah, this needs to be -2 because our coordinate system of our draw coordinates is in the top left corner. So we need to move 2 up. Then we create this 1 pixel by 3 pixels. So it's 3 pixel height and 1 pixel width. And yeah, I guess this is most likely already the arrow. So let's see. If I now press space, nice. We have an L-shaped tetromino there. Okay, cool. So now let's make it move. No, not the browser, but the Visual Studio Code. Okay, let's make it move. So in addition to a render function, we now need an update function on our board. So pub-fn update. Will update get a canvas actually? I don't think so. So that will definitely need a mutable self because we want to update something, and I'm not sure we need anything else. So let's move that up. So what we actually want to do here is for tetromino or tetromino in self.tetrominos iter mut, I guess. do can I actually extract? Will this actually work? We will see. X, Y. What do I need actually? I need the Y coordinate for updating, and that's kind of it. So let's see if we can actually do that. If I now do Y plus equals 1, this does not work, of course, because it's a reference. Can I do that? Maybe that's actually exactly what I need to do here. So now it should move down with every called update step. We will need to somehow limit that, of course, but let's see. So now if I go back into my update function here and call on the state board update every time it is running, so now it should maybe just go down. Okay. So now we have falling down tetrominos, maybe a little bit too quickly falling down. Let's just reduce the update limit. Where is it? The update cycle there. Let's just halve it from 60 to 30, and let's try again. Okay, yeah, that looks a lot better. So I can now create tetrominos. Okay, so now we need to somehow make them stop, actually, so that they are not falling endlessly. So I guess what we want to do is we want to introduce some sort of virtual bottom where they actually stop when they are falling into the screen. So maybe something like, where would we actually introduce that? On the board, I guess. So where's our board? So virtual Y stop, and that would be an i64, just to be in the same number space than everything else that we have. And when we create that now, let's just create that based virtual Y stop, like something, I have no idea, like 40, for example, and let's make a fix me here. Calculate based on terminal height and shown digits height to center display. So what we actually want there is in the future to calculate that based on the height of our digits that we are going to display in the end and our terminal size, so that they will actually somewhere end up in the center of the terminal, I guess. But for now, let's check that. Yeah, let's give our tetrominos a further flag, something like stopped Boolean, something like that, maybe, so that we can actually stopped false, so that we can actually stop them once they have reached this virtual position there. I'm already thinking about that we want to stop them first, and then later on we want to make this stop disappear, and then they can fall out of the screen again. However, we would need most likely something else there than a Boolean flag, some sort of enumeration which shows us in which state they actually are, if they're coming in or going out. Nevertheless, we can work with that, or we can think about that later. So now our update function, there it is. So for each of the tetrominos, we are having them fall down, and we only do that if the stopped parameter of them, so if they are not stopped, then we are doing that. And if the y coordinate is bigger or equal, I guess I don't need to dereference that for them for that. Self virtual y stop, then I want stopped to be true. Yeah, something like that. And this does not work. Why? Because I need to dereference it, I guess. Yeah, okay. So now this thing should, what's its problem here? Refutable pattern in for loop binding. Wait, well, where did I, that was not my intention. I wanted to change that here, actually. So, yeah, so we now have this information here where we actually don't even need the stopped information for the rendering. So we can just skip that there. And for the update, we need it, of course. Yeah, that makes sense. And I guess we don't want to do this when it is bigger, but only if it is equal the virtual Y stop. Because if it fell below it, then we want it to fall out of the screen. Yeah, maybe we will get away with a simple Boolean there as well. Okay, so let's see. Render implementation. Yeah. So we are rendering this thing now. Where are we actually creating this thing? It's down here in our keyboard handler, isn't it? Yeah. So what I want to do now is I want to create it at an X position, yeah, 20, and at position 0, so that it actually can fall in the whole screen. So let's see what happens now. Okay. Of course, we don't have any kind of collision checking yet, but it stops at our virtual line here, which is actually quite okay. So now let's work on some collision checking. How would we actually do that? We could compare all of the different tetrominos against each other. However, couldn't we just use the canvas information where we already have drawn tetrominos and where not? Actually, I guess we can. So so what we need here is something like if stopped and tetromino does not collide, or does collide, and we give this one I guess we need to give it then the canvas. So what we actually can do is we can give it the tetromino there. So yeah, that's a little bit. Okay, let's change this one to just get the tetromino here. We can then kind of simply extract tetromino. What did I want out of that? I wanted stopped, and I wanted, and I guess we needed to do it like that. Mutable stopped and Y equals tetromino. Does that work like that? I guess I need to remove that. Okay, so and now I can do does collide tetromino with a canvas, which I now need to supply to the update function. Okay. I guess I can live with that. And I don't actually need a mutable variant of that. So, and we don't have the does collide function yet. So, and it needs to be self does collide, of course. And we can actually put the canvas in here into the update function, because we get a canvas during the update function as well, in order to do just something like that, to read out the canvas data and do some updates based on that. So let's implement fn does collide. So this gets a self-reference, it gets a tetromino, and it gets a canvas, which is a canvas. And it returns a Boolean. So when would that actually happen? So let tetromino, we need the shape, I guess, and we need the X and the Y coordinates out of it. equal tetromino. Wait, can't I just do it like, can I do tetromino shape x, y? I guess that kind of should work. Okay, so, and by default, we will simply return false. So, but this one isn't happy. So because I guess I need to, wait, can't I do that? Express, can I do something like can I do, yeah, okay. This seems to actually work. Okay, so by default, we want to return false. And this is a problem still. What's the problem? Mismatch types. Expected tetromino, found mu tetromino. Yeah, okay, we need, we will give it a reference of a tetromino. So cannot borrow tetromino as immutable because it is also borrowed as mutable. Oh, that's a problem. Because we are iterating through those things, so we can't. Ah, okay, that's not good actually. That's a problem because I guess, yeah, that's the real problem. I cannot borrow self in this case. However, do I even need self? I don't think I need self. So let's call this does tetromino collide with canvas. Let's just write that out. Let's take this whole function and let's just put it outside of all of this because it should actually be not part, or should not need to be part of this. So now I can do, come on, where is it? It does tetromino and so on and so on and so on. And then I will put a tetromino and a canvas in there. And why is there a bracket? So now this cannot borrow tetromino as immutable because it is also borrowed as mutable. Immutable borrow occurs here. Okay, so that's kind of a... Why is that actually a problem? I know that we borrowed this information here, so we have a mutable reference to tetromino, and I just want to put an immutable ref. Oh, because, yeah, okay, I see. Yeah, let's think about that in a second. Let's for now just implement does tetromino collide with canvas, just to see if we can even do that properly. So we can do match on the shape because I guess the collision routines will be a little bit different for each of the shapes there. Yeah, I guess so. So let's fill up the arms here. Let's do the currently not necessary generic one there. Collision calculation for shape not implemented yet. And we just give it the shape. There we go. And then it will, yeah, it doesn't want the semicolon there. Okay, so now we need to implement that, and I guess what we could check is we could simply get the pixels out of the canvas and check if the I guess this function should be called would tetromino collide with canvas because we want to check if it would collide with the canvas if it's moved down one. Yeah. Okay, that makes sense. Would tetromino collide with canvas? So what we are now going to do is we have this L shape. So we actually have 2 points where it could collide with the canvas. So we have this L shape. So it could, moving down, collide at 2 positions, at those 2 positions here down there with the canvas. So no, I want to go back into my editor. So what we could do is something like, yeah, we could do something like return canvas dot, there is something like, yeah, get x, y. So what we actually want to do is, oh, yeah, those coordinates need to be within the canvas. So we would need to check. Wait, there was something like maybe get. Yeah, nice. So we have an implementation for that actually. Okay, that's actually quite nice. So let's do something like maybe get. So if maybe get the x and the y, which is the lower left corner of this thing, if this is not equal, so what are we actually returning there? We want to return true if it collides. So if this is not equal kind of an empty color, so let empty color from RGB, so we have a black background. This would actually be our empty color. This is kind of a hack, but I guess it could work. So if this and I guess we need to wrap this in a sum. So if maybe get is not sum, is not empty, or x plus 1, so the one right to the lower left corner is not empty, then we return true, because then it collides, I guess. And something it does not like here. I guess it does not like the... It does not like the braces there. Okay. Do we even need this return there? Can't we just... Okay, why do we need that? Because of the panic? Maybe. No. I have no idea. Okay, so let's add, oh, because I have the false at the end. Okay, yeah, makes sense. Okay, so now we actually should have something that can calculate the actually we don't need that, and then we don't need the return. Yeah, okay. Can actually calculate the collision. So it should now be able to calculate that if we fix that problem here. I mean, is it because we extracted this stuff? That could actually be the case. Let me see, tetromino.y, and because essentially I'm not sure why this should not work. Not sure that Tetrominos stopped. Yeah, okay, then it works. Yeah, I guess the problem is there that we cannot borrow it as immutable at this position, because we have still references on it which are mutable. Yeah. Okay, this kind of makes sense, I guess. So, however, now we should be able to stack those things on top of each other if we have. Okay, we did something wrong there, I guess, because it's immediately stopping. So, what did we do wrong there in our most likely calculation there? Oh, I see. We should have checked y plus 1, so 1 down from the current position, because of course otherwise it would collide with itself. So okay, so now the moment of truth. Nice. Okay, this at the top here is a problem because we are moving them down and then checking it. No. Okay, that's strange why this actually even happens there. Not sure why it can happen. So now if I add this one, it should add it and then try to move it down, and this should already collide, so nothing should happen, but it does. Okay, so there is some sort of error still there. So we have the x check and we have the x+1 check. So this should actually work, but it does not. So if it is not empty or if this is not empty. So in both cases, it should collide. Interesting. But it only happens at the top. So I guess there is something wrong with it that we can figure out later. So let's not think too much about that. Let's maybe go ahead and make this create a tetrominos at random positions, and then let's quickly add more tetrominos. So I think we are creating those down here somewhere, aren't we? Yeah. So we now have tetrominos, so we are always adding this at x position 20. But I guess we can simply do something like get the engine, get the random component. We actually have a random number generator in our engine that we are propagating through this engine environment thing here. So, and now we should be able to do something like get range between 0 and the width of the terminal, I guess. And then this does not work. No method. Oh, I guess we need to import. There is a method genRange with a similar name, genRange. What? Oh, did I? Oh, I need to. First of all, I wrote it incorrectly, and then I needed to import the corresponding trait. So what's the problem now? Expected I64 font U32. Yeah, because the width is a U32, but it is expected to be an I64. So, but we can convert that. And we need to subtract one. Yeah. Okay. So now it should actually, at every space press, create an L shape at a random position on our screen, and all those should fall down. Okay, that's actually quite nice. And they are correctly colliding here. At least it seems. Even if they stack in this L shape, which happened here, they are colliding correctly. Actually, yeah, there as well. Okay, that's actually quite nice, and there as well. So this works as it should, I think. Okay, so this is actually a great position there. So we have already done our basic falling down and collision detection system. So maybe we could add some more shapes, like for example, why not the block, and some other one. Maybe this T thingy here. I have no idea. They have specific names. Maybe we should look up the names because they have names. So straight, square, T, L, and skew. Okay. Okay. Yeah. Then let's maybe call them like that. So this one is called square, and this is a T shape. And what was there? Straight. No, come on. Straight, and what was the other one? Skew. Okay, and then they can of course be rotated. Yeah, that's something for another day, I guess. Skew. So maybe we should just call them not L shape, which is a kind of double in that. So let's just do L, square, T, straight, and skew. Okay, those are the tetromino shapes that we support. And yeah, now we can actually create, let's see, when we do randomization here, when the space key is pressed, let's extract those randomizations out. So let X is equal this randomization here, so that we can actually put the X in there. Let's maybe randomize the color as well. So let color equal, currently this is this one, but let's just go ahead and have this one like rand gen. We could just have it generate a U8 for us, I guess. And then we want that. We want that 3 times. Like this, and then we would have a color here, I guess. And we need a tetromino shape, so let shape equals if I don't want to generate the whole set, but I now have defined the whole set, which is a little bit not so great. Okay, so we are just generating an F64 here, I guess, and if it's less than 0.5, then we will simply return tetromino shape L, and otherwise we will give it not a termination, but a tetromino shape, I don't know, straight. Or we wanted the square initially, so let's do square here, so that we only need to implement square next. And then I guess I will just put the shape in here, and we will be a happy camper, hopefully. So now if I start that, it should most likely crash, because it will, okay, it generated, okay, and then it crashes because collision calculation for square shape not implemented yet. Yeah, that actually makes sense. Okay, so let's quickly implement the render and the collision detection. So the render for our tetromino shape square should be reasonably easy, I guess, because that should actually be a filled rect, which is x at the x coordinate, and the y coordinate will be -1, and we will have a width of 2 and a height of 2. And that should actually already be being all that we need. Now we need the collision detection, which is somewhere up here. Okay, so let's do tetromino shape square. It would of course be nice if we could check now against a field. We can check against the range, but yeah, let's just let's do canvas, maybe get, and let's do x. Yeah, we are in the x coordinate space, and then we have y -1, -1 +1. Wait a second. Is that actually correct? Oh, yeah, okay. Y plus. Oh, we only need to check the down thingies there. So essentially, this is exactly the same. Nice. Because we only need to check the 2 down positions. Yeah. Okay, makes sense. So now we should actually be able to know. Let's get back to our terminal. We should be able to know that was the wrong command. We should be able to generate squares and Ls, and they should actually collide with each other. That actually works out already quite well. So yeah, I like that. I like that very much. Okay, we will need to implement rotation and stuff like that, but that's actually quite nice. Running in our terminal. Okay, so let me quickly flesh out the other shapes in exactly the same manner, but I guess I will just fast forward that for you because it is exactly the same than we did before. So let me just do that quickly. Okay, so I guess we hopefully have all of them if I didn't miss something there. And yeah, let's see. So, what I need to, it's still only generating squares and L shapes. So what I of course need to do here is change our, where is it? Random thingy there where we generate these shapes. Yeah, exactly. So our shape now should be the engine rand gen, and I'm not 100% sure. Can we actually give it a can we give it an enumeration and it will generate us one of those? That would actually be quite awesome, but I don't think that we can. Yeah, I don't think that this works. Because we need to do it ourselves then. Okay, so let's generate a range here between 0 and how many do we now have? 1, 2, 3, 4, 5. Okay, that's not that bad. Gen range between 0 and 4. No, 5. And we want range there, and we want to actually match that. And we are going to do, in the case of 0, we will give it a tetromino, tetromino shape of the L, yes. And in the case of 1, we will give it a square or something like that. In the case of 2, it will be a straight. In the case of 3, we only need this for testing purposes, so I guess I can just, oh no, T, I can implement that here. So, and what is the one we are missing still is skew, I guess. So, and does this work? It does not. Non-exhaustive patterns. Wait, what? Yeah, but we only get a range between, come on. Yeah, I guess, but it does not make sense to have this one, so we simply ignore it. Okay, in case we get something very strange, we can panic, I guess. Something very strange happened. Or did it want to warn me that I had the range set wrong? Okay, this looks kind of good. We could kind of implement Tetris with that. I like that. I like that very much. So actually, we can create a lot of tetrominos. So is everything there? Is there? This is a skew. This is a straight. It's a T. It's an L. There is a square one. So they are all here. Okay, I guess we have the main thing needed for us to implement our timer / clock in the end there. We have the basis for that now ready. And now we only need to figure out how to mount these together in combination with rotation. We need to be able to rotate them, but essentially it's not a problem. It's the same thing, but rotated. And then we need to figure out for each of our numbers how to put them together with tetrominos, and to simply encode that and then let them fall for each of the numbers we want to put there. Yeah, but I guess we can do that, or we will do that in the next session, because this one already got a little bit long. So yeah, I hope you enjoyed watching me implement a quite simple kind of tetromino-like block falling thingy here in our console. This is, as you can see here, this is actually a Tmux running within an Alacrity terminal. So this works out exactly as it should. And I'm already looking forward to the next session where we will implement our clock. So if you like this and you want to be informed when the next session is out, please hit the subscribe button. And as always, please hit the thumbs up button if you like that, because that always helps with the YouTube algorithm. You can comment to any of my videos. I will always try and answer all and every of your questions or comments. And it's always appreciated if you communicate with me and give me some feedback. So thank you very much for joining me on this session. And I see you on the next one, I guess. Bye.